few. Does anybody have any trouble? They don't come across as, well, what is it, Gene? When? Dot dat. When mail dot dat. They don't? Okay. That's what's happening with the distance learning students. And we're just finding out now. I'm finding out now about it. Okay. All right, so this is our final problem set for this chapter. We'll be starting a new chapter tomorrow on bars. So we've got more to do on strings. This is the last problem set on strings. The first problem is a Fourier problem. We have a string under tension, some length L, it's fixed, and at time t is equal to 0, it's plucked, it's pulled aside from equilibrium, and at time t is equal to 0, it's released from rest. So that's a classic plucked case, as we've seen before. And what makes this problem interesting is that it's not done symmetrically, it's off-center, it's 1/3 the way. All right, so we're asked here to, and I commented on this in the problem set assignment. We basically want to find the modes that are excited here. So you know that there's going to be the motion here can be represented as a superposition of the normal standing wave modes. So we need to find out at time t is equal to 0 what the amplitudes and phases of those modes are. And this is the standard way to solve this. You know, now that I think about it, you probably could solve it with counter-traveling waves. But anyway, this is one way of doing it, using the Fourier analysis here. So here's the fundamental or lowest frequency mode. It's going to contribute. Here's the next mode up. Looks like that's going to contribute. Look at the third mode. Okay, the third mode has a node where it's been plucked. So this will not be excited. This mode will not be excited. And in fact, any mode that has a node there is not going to be excited. So it's the 9th mode, the 12th, etc. And if you don't see this, I have funny feelings. This may not be quite rigorous, but it's just very reasonable that if it's plucked here, you're not going to be able to excite that. It emerges in the math, of course, when you do the math here, that the 3rd, 6th, 9th, and 12th, etc. are not excited. So here's the Fourier analysis. We know that these normal standing wave modes here, their amplitudes are constant in time. These modes do not interfere with themselves. We know that because their amplitudes are constant. They're not coupled, is what we say. They all look like sines because with zeros at x equals 0 and x equal L. So we get this discretized wave numbers here, as we've seen before. And the relationship between the frequency and the wave number is, of course, omega is equal to ck. So our function here is straight line going through the origin for this side. So this works. Now you have to play with this a little bit, right? See what I did here? I know that at x equals 0, it's 0, and at x equals L, it has to be h. At x equals L over 3, it has to be h. So you can see that this works. And similarly, it's a little bit more trouble, but you can do the same thing over here. It's got to go to 0 there. So we're going to need an L minus x. That's clear. And again, at x equals L over 3, we've got to get h. So this does it. What about all of the b coefficients? They have to be 0 because at time t is equal to 0, we have no velocity. We take the partial derivative with respect to time, set it equal to 0, and the only way that's going to be is if all these b's are going to be 0, because this becomes the cosine of omega in t. So we just have to worry about the a's here, and we invert this, the standard Fourier inversion. using the orthogonality of the sine functions, we get this. Okay, now, this is we're not going to go through all this. Takes time to go through this calculation, but it's good to do once. And I did it. I already did mine. I was an undergraduate many years ago, and I still remember doing this problem. It was on a mechanics course. So it's one of those problems that sort of builds character, sometimes what you can say. Because it's not symmetric here, it's a little bit of difficulty. But I encourage you to go through it, and you only need to go through it once in a lifetime. We can set it up a little more here. We substitute in. Our function is defined piecewise here, from here to here and here to here. So the integral is going to split into two integrals, as you all know. And we get this one and this one. Now you're not going to have this one of them being equal to the other, right? The symmetry's broken here. So you have a lot of integration by parts terms here, right? Here's one. And also what complicates this is that this term, often it's 0. You're going to find it's not 0 now. Okay, I made a comment on that here. So there's some work between here and here, and I encourage you to do it. It's up to you. The problems are for you. This is the result if you carefully go through this. And to be honest with you, I don't think anybody gets it the first time. You know that when they're working at the problem, they usually have to go back and find errors. It's just tedious calculation. It's easy to make a mistake. So don't feel bad if you don't get this the first time through. You need to go back and I don't think that's unusual. And oh, by the way, look at this. When n is equal to 3, what's the amplitude? What's the sine of pi? 0? Yeah. So all of these, that's a check. Okay, any questions about that one? Okay, the next one is, this is simple, but it's a useful way to look at systems. Oftentimes we're dealing with some system and we need to modify it maybe for practical purposes. This happens all the time in the lab. So we want to see how, for example, how the frequency, this problem addresses the frequency of the fundamental, it looks like. Yeah, so we're just going to focus on, but you can look at other modes too. Okay, how does the frequency of the fundamental change with the parameters of the system? Well, first of all, and this is going to be related to changes that we would actually make in the laboratory, like the tension and the density. We can vary these in the laboratory. So the speed, of course, for waves on a string is square root of the tension divided by the density. The fundamental looks like this. Okay, half a cycle later looks like this, vibrating back and up and down. The wavelength is twice the length of the string. And how do we get the frequency? We want to address the frequency here in this problem. Well, the frequency is just the speed of waves over the wavelength. The wavelength is 2L, so we can substitute C. So here are the two relationships we're going to be dealing with. Here's how the speed of sound depends upon the parameters of the tension. We have three parameters here: tension, mass per unit length, and length of the string. Those are the three parameters. So this is how the speed of sound depends upon those parameters. Here's how the frequency of the fundamental depends upon those parameters. I'm not going to use the prime notation that they use there. I don't think there's any need. What we want to address here is what happens to the speed of waves and the frequency of the fundamental when the length is doubled. Okay? So, often you can answer these without having to do this. For example, if I keep everything the same, but I double the length, how is the speed of waves going to change? It's not. It's the same. And the proof is right here. We haven't changed the density or the mass per unit length. So under this change, this implies that C doesn't change, C goes to C. But the frequency, what's going to happen to the frequency? It's going to halve, right? If we, because right here, we're keeping the tension and the density constant, we're doubling the length the frequency is going to have. All right, so that's the idea here. The next one is the density goes up by a factor of 4. And this can be achieved, incidentally, and it's related to another part here. If you double the diameter of the wire, or the string, whatever it is, why does the mass per unit length go up by a factor of 4? If you double the diameter, what happens to the cross-sectional area? Yeah. So the area, if you double it, the cross-sectional area is going to go up by a factor of 4. So what that means is the mass, what did I just, yeah. So this, if you double the, yeah, so I'm sorry, I'm mixing these are related. So we're asked what happens if the density goes up by a factor of 4. And this is not unreasonable because if you double the diameter, that's one way to achieve this. So what happens to the speed of waves? It's going to get halved. More inertia. It's going to get halved. What's going to happen to the frequency of the fundamental? Well, it's going to get halved. We're leaving the length and the tension the same. Here's the cross-sectional area doubling. Right? That's going to double the mass per unit length. And now if you look at this, you'll see that the speed of waves is going to drop. There's more inertia. You know it's going to go down. It goes down by the square root of 2. And similarly, the frequency drops by the square root of 2. If you have the tension, what's going to happen? Well, the speed of waves is going to go down by a square root of 2. And the frequency will go down. Both of them will go down by the square root of 2. And finally, this is what we talked about. That's essentially this problem here that we talked about. So we get the same results as we got there. Okay, so again, this is just kind of a useful thing people do in the lab all the time. Sometimes it's just to get a feeling for the system. Sometimes you need to. Often, you know, things aren't going well, which happens all the time in the laboratory. Most of you will find this out when you do your thesis research. So you're just trying to make the next step, and sometimes you need to change your system. So it's useful to think in terms like this. Any questions about that one? Okay, the next one is 11.1. Okay, so this will look familiar to you, right? Because it's something similar to it on the quiz. But it's different, but it's not the same. The problem here is this is an undriven, undamped system. We want to find the normal modes. And the normal modes are just the standing wave modes of definite frequency. So maybe I better look at this again. Yeah, and we're going to take the special case here where the stiffness here equals the tension in the spring divided by the length. Note that those have the same units, right? Remember, stiffness is from Hooke's law. It's newtons per meter, force per unit length. So we get the same units. We're taking the tension here and dividing by the length. So we know that that's going to be, well, let's wait until we do the calculation. Okay, so what do the modes look like? Well, they're going to be sinusoidal because they have to satisfy the wave equation. They're going to be standing waves, sinusoidal waves. We have to have a 0 here, and here we're going to have to do something to get the boundary condition here. So before we worry about that, let's write down what we know. It has to be a standing wave that satisfies the wave equation. It has to have definite frequency and be 0 here. This is it. It's going to look like that. So we've seen this before, and we're going to keep seeing it. I told you that it's a good idea just to start thinking in terms of this. You know, just write this down. You can see that it's a standing wave. It has the space and the time separated, right? It's not a traveling wave, like going one way or the other. And it's obviously satisfies the wave equation, and it's zero. The displacement is zero at x equals 0. Now there's the next thing we need to do is impose this. There's a boundary condition here, and you can use impedance, as I mentioned here. You can use it. In this case, I think it's easier not to use impedance. Just use Newton's second law. So let me explain that. This point right here, there are two forces on this point. There's the force of the spring, and there's the force of the string, right? And we're talking in the transverse direction here. So the spring only exerts a transverse force. The string will exert a force, will have in general a component along this direction, and that's all we care about. I haven't notated it here, but to actually do this, you're going to have to balance the longitudinal tension component. It's going to have to be balanced somehow, right? Because otherwise you'll torque this thing over. So you have to have, and we've talked about that. There's ways of doing that. So we have to have net, because there's no mass, it has to have net force of 0. It has no mass and it's undergoing simple harmonic motion. So the force has to be 0. We've talked about that probably too much. So you recognize this? This is the slope times the tension. This is going to be the transverse component of the tension on that point. And I need a minus sign here because when the slope is positive, it's going to be that way. So I need a minus sign. This is Hooke's law. This is the force of the string. And this has to be 0 for all time at x is equal to L, at this, of course, at this point. So we take our solution here and we substitute it into here. The amplitude is going to cancel. This is going to gives us no information about the amplitude here. But what it's going to do is discretize. Right now we can, we don't know what omega or k or equivalently k is. But this is going to give us a spectrum of frequencies. So we substitute this into here. And if you just stare at it, you'll see that you can get this. Okay, cancel the amplitude and you get this. And now, this is made easier on us than the quiz problem. I know some of you are having a little bit of trouble. The standard step here, once you get this condition, this is only, oh, by the way, I need to repeat this. This is only going to be true for certain k values. The k values have been discretized here. Those are and from those we get the frequencies. Those are the normal modes. They are the standing wave modes. So at this point, the appropriate thing to do is multiply by L over L, because the dimensionless variable we need to determine is KL. And then you beat it in, it's not difficult in this case, beat it into a form. And I want you to do that on the quiz, right? If you have trouble, come by and see me. Now, in this case, we're just going to go ahead and substitute in what S is. We're given that S is T over L. So if I substitute that in there, this is the equation we get. And what kind of equation is this? Kind of strange name for it. It's a transcendental equation. It cannot be solved analytically, but we're going to solve it numerically. And we're going to do that today, now, soon. But first, let's do the graph. It's always a good idea to do the graph. Here's the equation, right? So just go ahead, let's start thinking of this as x, because that's what I'm going to use in the next page. This is our unknown, this combination here. Think of it, let's call it x, dimensionless number. We want to find where the tangent of x is equal to minus x. So we draw the tangent branches here. These curves represent the tangent of x as a function of x. The right-hand side is just minus x, which is this line of slope minus 1. And those intersections correspond to the solutions. So here, we're satisfying the equation. So once you know those points, by knowing those points, what we mean is you read up here, that value of x here, okay, that's going to be one of the, give us one of the frequencies, and etc. here. So you'll notice, and this is one of the reasons the graphical sketching the graph is useful. You'll notice here that our fundamental has to have a KL value between pi over 2 and pi. Right? Now, and similarly, we're going to solve for the, what do we do here? We're going to find the first two modes, the frequencies of the first two modes. Well, we're actually going to do one. I'll let you do the other one if you want. But the reason I'm pointing this out is the fact that it exerts a range here. We know this is where we need to start in this range to find this. And this is true for the method we're going to use, the calculator method. But it's also true on the computer. If you shove this on a computer, there are an infinite number of solutions here. So I don't know if there are programs that'll spew out all of these, or you have to give it some starting value, give it some range or something like that. So one of the nice things about the graphical method is that we've got ranges in which those solutions have to lie. So I encourage students, even if you need to do this accurately and quickly and you want to use a computer, it's good to still sketch this so you'll know where these modes are. Okay, so again, the first mode has to lie in this range, the KL value. So here's the idea. This is like roughly 3, this is 3/2. I started at 2. That's the and I didn't know the answer or anything, okay? But I know I want to pick an initial value between, roughly midway, but somewhere between these two values. So I chose 2. So I wrote it down, I form a table, I write it down, and then I evaluate minus the tangent of x. Okay? Where x is in radians, by the way. And I get this. So what do I need? So it doesn't solve it, right? But it's not that bad. What do I need to do to x to try to get? It's not going to be, the root is not going to be 2. What's it going to be? Less than 2 or greater than 2? I need to increase it a little bit because this value is greater. So I need to go up a little bit. And because it's pretty close, I just went up by 1/10. This is all, it's up to you, I think you could put a 3 here if you want, but it seems kind of crazy because we're pretty close, right? So I did a 2.1. And oh, look at that. Now I'm over. So I overshot it, right? So I'm going to go back to here. And it's up to you. You can pick whatever you want to. I think it's going to be closer to 2. So I incremented it by, by 200ths here. Incremented this by 200ths. And I get this. Oh, it's not bad. I'm still under, right? So I went to 3. Oh, now I'm over. Okay, so this is the process, and you can keep doing this. You can just zero in, and you can get to any accuracy you want to just by doing this. And usually, 3 figures. I got roughly 4 figures here. That's usually fine. So this goes, once you do this a few times, it's pretty quick, and it's actually I think it's fun. I don't know what you think, but. That's the method. And we will use this, we're going to use it today and I think elsewhere in this course. And it'll come up, the idea of doing this will come up in the next course too. Because we're going to, in acoustics, we're going to encounter, sound in fluids. We're going to encounter this transcendental functions. So, all right, so what is the... First, so you can do you can do a similar thing. You just start off in the region for the second mode. Same idea. So I strongly encourage you to do this because I could talk about this for an hour and it's not going to sink in. The only way it's going to sink in is if you just got to do it. Okay? So what does the first mode look like? Well, it's pretty clear it's going to look like this, right? No nodes. Because you know that when the spring becomes, we're at a specific value of the spring constant here, but we can certainly imagine changing it, keeping the string the same. And we know that when it's very stiff, it's going to look like this. And we know that when it's not very stiff, it's going to be a half wavelength. It's going to be a quarter wavelength when it's not very stiff, right? So it's going to look something like that. The second mode now will have to have, there'll be an interior node somewhere, and it'll look like this. And in this, in this, so this is, we're going to stop with, that's what we're going to do for this problem. But I should point something out here, because it's a good check, and I didn't write it down here. Okay, if you really want to use impedance, here's what you can do. I picked this up from Professor Baker. I think it's crazy, but you can do it. You can go back to the beginning of the problem here. You can imagine that you're applying a force here at this point, right? You can write down the impedance seen by that force. So that's actually on the quiz, isn't it? Yeah. Okay, so it's just, you have to flip it. It doesn't matter, right? And then what do? You look for resonances. Set the reactive part, and the impedance is going to be purely reactive here because there's no dissipation. You set it equal to 0, and those resonances are identical to the standing wave modes or the normal modes. So what you're going to find is this. It's a different way of deriving that. Okay, or this. This is what we acted upon. It's really this equation right here. You'll find that. So that's probably a little quicker, but I think it kind of takes the fun out of it. It's up to you. Okay. So that's so there's actually two ways. You can impose the boundary condition. We talked about this in lecture with impedance, and then you can also do this trick here, which I think most people don't see, and I certainly didn't see it. Why would you want to add a drive? But it works. It does work. Think about it. The resonances are going to be the standing waves, so you can do it that way. There's one more important thing I want to say. More important, I think. What's the wavelength here? Well, it's got to be between half a wavelength and a quarter wavelength. Right? That's actually, you can get it, it's mathematically embodied in here. So it's a good check on the solution that the wavelength is greater than this, it has a half wavelength is greater than L. And you can see it here, right? Because this point's going like this. A half a wavelength is going to be too short. Half a wavelength between the 2 points here over the length L will be too short. And similarly, these other modes. Okay. At this point, we're really getting into it. This is physical acoustics, right? I know it's not sound in a fluid, but physical acousticians do stuff like this. I think I told you guys, they do more than just sound. Surface waves, waves on bars, that's really considered to be part of acoustics. The special case of what's called physical acoustics, the fundamental of acoustics. So there's a lot of mechanical wave systems are dealt with by physical acousticians. Any questions on that one? Now, this is something I don't think we've seen before, have we? I can't remember. So we have a string here, and there's a mass. We're going to assume it's a point mass that has a negligible extent, okay, spatial extent, midway. And the problem is to find the frequencies of the first 3 modes. And again, we've used this word normal in this chapter. Most acousticians just say standing waves, standing wave modes. Okay, so what's the first thing you see here? This will help. Just kind of a sketch of what's going on here. And you will always want to, I think it's a good idea to do the simplest things first. Try to make some progress, right? What do you notice here? All the even modes. The mass is at a node, so does the mass make any difference? No. Yeah. You're going to get the same mode whether the mass is there or not because it's at a node. So that's good. We just took care of half of an infinite number of resonances. We know that this is going to be unchanged. So let's go ahead and calculate. Part of the Yeah, the problem is to calculate. Let's calculate this frequency here. So this is easy. It's the speed of waves, which we can calculate because we know the tension and the density. And the wavelength here, the length of the string is one wavelength. So I'm going to substitute for lambda 2 the length of the string. And I punch it in and I get 158 hertz. So that's simple, same value as whether the mass is there or not. So how do we handle these? So do you think this is a sine wave? I tried to draw it. I mean, what do you think? We've got a mass here undergoing simple harmonic motion, right? There's got to be a force causing it to do that. So it has its greatest acceleration. If this is the turning point, it's got its greatest acceleration right here. Each is good. The wave will be symmetric, but it has to come in with non-zero slope here. It cannot come in with zero slope because we have to have a net force on that mass. So here's the way I encourage you to think about this before diving into the math, which students love to do, right? What's going to happen to the wavelength here compared to the case where there's no mass? When there's no mass, we have a nice half a wavelength here, a sine wave, right? What's the wavelength going to be here? Don't look at me. Look at what's it going to be compared? This compared to the half a wavelength. I can see maybe what the problem is here. We can imagine just extrapolating this, right? This is a sinusoid. It's got to be because it's satisfying the wave equation. It's longer. Who said that? Right. So if I extrapolate this here, forget about what's going on here. Just take this. It's going to end up over there. So what is the frequency of this mode going to be? We can now qualitatively argue what the frequency how the frequency of this wave mode is, how the frequency of this mode is going to shift due to the presence of the mass. What's going to happen? It's going to go down, which we could have guessed initially anyway. When you add inertia to a system, I think always, or maybe almost always, it's going to lower the frequency, right? But we've looked at it from a deeper, we can see why, specifically why here. The wavelength has to go down. See, before, without the mass here, this is going to be half a sinusoid. Now, because that slope, it doesn't come in flat, it comes in like this. The wavelength here, and therefore the frequency, will be lowered. And that's going to be true for all the odd modes, clearly. Right? See it? Okay. So now let's calculate. There are two forces at any point here of the motion. And just look at this one right here. Assume this is just any point of the motion. We have two forces here. They're both going to have the same, by symmetry, they'll have the same tangential component, which will be minus, we just talked about this, minus t times the slope there. We just talked about that in the previous problem. I need to double it because we got two forces here, right? Two strings on either side. So that's the force. By Newton's second law, the force equals the mass, this is our bead of mass that's been put on there, times the acceleration. The acceleration is the second derivative with respect to y, evaluated the midpoint there. And of course the acceleration of the mass is the same as the acceleration of the string at that point, right? Because it's attached to the string. So you can see where this is headed now. We do a similar thing that we did before. We take, I didn't write it down. Hold on here. Oh, I guess it's not here. Oh, sorry. What's this going to be? It's going to be some amplitude that we don't know or really care about times the sine of kx times e to the I omega t, just like the previous problem. And I guess I didn't write that down. So the y to the and all by symmetry, we just need to worry about on the left-hand side. It's easier. So it's going to be y is going to be a times the sine of kx, and then that multiplied by e to the omega t, just like the previous problem. Okay, we substitute that in here. The amplitudes cancel. It's independent of the amplitude. Sine turns into the cosine. And remember, we have to evaluate this at L over 2. This is a condition at L over 2. And so you know what's going to happen here. Right? You can see it coming. We need to simplify this. The natural thing to do is put the cosine under the sine here. To get the tangent. Put everything else to the other side of the equation, and then start to simplify this. Omega is equal to ck. The unknown is kl, so I'm going to get rid of the omega, put in ck, simplify, and then you'll notice here our unknown. The next thing I'm going to do here is, you would think would be multiplied by L over L, because then we get the combination of kl. That's our unknown, right? Okay. Now you'll notice, why did I do this? Why would somebody, why would we go from the tangent to the cotangent? What's convenient about that? You'll notice our unknown is downstairs here, right? If we plotted our tangent branches here, this would be a function of 1 over, it would look like this. Now we can deal with that. You can deal with that, and that's permissible on the quiz, and so I'm going to give full credit for that on the quiz. But here, because we are going to do this on a calculator, it's a good idea, instead of dealing with this 1 over function, okay, which comes from here, that's going to be a KL, to go the other way, and it just kind of flips the cotangent branches are very similar to the tangent branches, and it turns that into a straight line. That's much easier to deal with here. Otherwise, we'd have to have another column here of 1 over alpha, well, you don't have to, but it just makes it easier. So that's what I did there. I plugged in numbers. All that's important here is the mass compared to the mass of the string. We've seen that before. We're given numbers. So in the end, here's what we have to solve. There's the transcendental equation we have to solve. Once we find these alpha values, we're essentially done, because that means we're going to know KL. We can use omega is equal to CK to find the frequency spectrum. Okay, so again, here's what it looks like. Here are the cotangents. They diverge at, interleaved points compared to the tangent. So you always want to check that, make sure that you're not screwing up. And the intersections, we care about the first two, so that's why I guess I didn't put a dot there. We want to find these, and you can see that the first one is going to be between 0 and pi over 2. Second one's going to be between pi and 3 pi over 2. Okay, so again, here it is, and here I wrote out the second one. So we've discussed this before, and the only way you're going to learn it is by doing it. And you might want to do it a little different way. It's up to you. And so I get to four significant figures. Maybe the fourth is not, maybe it's off by plus or minus 1. I don't really care, right? We don't care. So, well, it looks like that was nailed. Okay. So anyway, yeah, so I think it's accurate to 1,000. Looks like this one, maybe this one too. So once we know the alpha values, here they are, pretty precisely. As I mentioned before, we can get the frequencies. Omega is equal to CK. We get rid of K, and then F is 2 pi divided by, omega divided by 2 pi is F, or in other words, omega is equal to 2 pi F, right? So we can invert this, and we can find the frequencies. Okay, for the first mode here, the frequency is 54.2 hertz. And I threw this in, you can see I threw this in later. It's easy to calculate the frequency when there's no mass. It's just the next mode up. I mean, it's just like we did we can calculate this frequency. We can find the frequency here when there's no mass. And that is 79 hertz. So it's a significant dropping. Adding that inertia to the system has significantly lowered the frequency. Right? You can see 54 compared to 79. And then the third mode, I get similarly, so we get this. Oh, I hope there's no confusion here. The second root here corresponds to the third mode, right? So, I don't know how to, a little bit of a problem here. Remember our physical system here, we're solving, we don't need to worry about these modes. So in our solution, approximate numerical solution of the transcendental equation, we're just dealing with the odd modes. But I called this, for the solution, I called this number 2, the second solution. So you guys really get, you're gonna, this now's the time to learn this. You got to do it, you're doing it twice, right? There's 2 problems that involve this. And again, contact me if you have any trouble or if you see any mistakes, let me know. Okay, any questions about that one? Okay. Oh, we're at the final problem. Okay, good. So we did some energy work. We finished the chapter by talking about energy, right? Always important. So that's the purpose of this problem, is based, although it doesn't look like it in the beginning, but that's really the purpose of this problem, is to get into energy. And I think you might be surprised by what the behavior is here in this problem. So this is 12.2. So we have a standing wave. We have a standing wave on a fixed string of length 31.4 centimeters. What do you think when you see that? Can anybody give me the length to 4 figures? It's pi, right? So this is what some authors do in KFCS. They love to do this. It's probably happened before. You guys, has it happened before in the book? Have you? I think we've encountered that. So what they really mean, and they should have just said this, is to get to the point and to be more accurate. This is rounded. It really is 10 pi. So you should think of the length as, all right, who stole my chalk thing? I guess I didn't bring it again. So you really want to think of the length here as being 10 pi, and this is all in CGS units, centimeters, grams, seconds. We're going to do this problem in CGS units, okay? So that's what you should really think of. And they just do this it makes it easier, that's all. Because there are naturally pi's floating around, and they're going to cancel. By choosing the length to be proportional to pi, we'll be able to cancel the pi's. So it's just kind of an annoying trick, but it does actually make it simpler. We're given the density. Again, this is CGS units, right? The linear density. And here's the wave that we're given. Okay, where everything's in CGS units here. So x is in centimeters, t is in seconds. And the amplitude is in centimeters. So, how do we proceed here? That's all we're given. And we want to know, I don't know what they're asking for, but to make any progress on this problem, we've got to identify the mode. It doesn't matter what they're asking. We need to identify, this is obviously a standing wave mode. So we need to know the parameters of that mode. For example, what mode is it? Well, to get that, you'll notice here that omega is 3 in CGS units, and k is 1/5. Because this has the form sine of kx and cosine of omega t. So what can we do with that? Well, the ratio gives us the speed of waves, right? So usually we go the other way, but this is what the information we're given in this problem is. So this is going the opposite way. And because omega is equal to ck, we can find c, and it's 15 centimeters per second. The frequency is 3 radians per second. So we want to put that in hertz, so we divide by 2 pi. So the frequency is 0.48 hertz. We can identify the mode by looking at the wave number. It's 1/5 inverse centimeters. And remember, k is always 2 pi over the wavelengths. So we can determine knowing k, we can find the wavelengths. And the wavelength is 10 pi. So what mode is it?
First one.
No, it's not the first. Yeah, I know. It's easy to think that.
Well, that's right. Last one.
Yeah. So what it's going to be, because this is 0 and this is L, and the length equals, it's going to be the second mode, second harmonic. Looks like this. Kind of like that. And half a cycle later, it looks like that. Okay. So part B here is oh, incidentally, I'm sorry. We're given the amplitude here. So we know the amplitude of this wave. All right, okay. So we're asked in part B, what is the amplitude of the particle displacement and speed at L/2? So what's the amplitude? It's 0. Okay, what's the speed? 0. They didn't ask, well, I don't know if they asked for that, but the speed's obviously 0. It's a node, okay? Now this is more interesting. What about L/4? Well, you can see now, this is important, that's why it's important to identify the mode here. Because it's obvious, once you see this picture, that this is L/2, at L/4 here, we're going to have an antinode, right? So, we can get the amplitude. It's simply going to be this, because I've identified it as the antinode. So otherwise known in a standing wave as the maximum amplitude. You know, the amplitude at an antinode is the maximum amplitude. So, and if you don't believe me, you can calculate this. Look at let x be a quarter of the length, and you're going to find it's 2 centimeters, the same as that number. But we know it has to be because it's an antinode. And this amplitude that sits here is the maximum amplitude of the wave. What about the, don't they ask us for the velocity? Yeah. What's the, oh, so they do, yeah. So obviously at the midpoint there, the velocity amplitude is 0. This is going to have some velocity amplitude, and we can get it. We have the waveform here. We just differentiate it with respect to time, and then evaluate it at x equals L/4, and look at the magnitude of the magnitude of that, and it's going to be 6 centimeters per second. Okay, we'll need these numbers for what's going. We'll need this and some of these other numbers for the next part here. Okay, so this is where it gets interesting. In part C, find the energy density at these 2 points. Okay, so this is, we derived this in class. This is true for a string. Always true for an ideal string, right, under ideal conditions, for a linear string. This is the energy per unit length. This always works, okay? So you plug in the numbers here, and here's when you punch it in, here are the results. First of all, at the midpoint, and this may surprise you, the energy density is oscillating. It's going back and forth between 0 and 1.8 ergs. Remember, we're in CGS units here. And L/4, it has the same maximum value, and it's oscillating in, and they're 90 degrees out of phase. So what is going on here? Here's this little diagram. Well, we can use this. So what's going on here? Let's say this is a turning point of the motion right here. Okay? In time, it's going like this, right? So what's the energy right here? Is there any kinetic energy? No, there's never any kinetic energy at a node. But is the string stretched locally? Yeah, remember, we're in our approximation here, the displacement is transverse. It's transverse displacement. So if you take two little points here, right, and you look at what their displacement is for this, they get stretched. So there's potential energy in there. And that's what, so at this, even though this is a node, what this represents is the pure, there's no kinetic energy contributing to that, it's pure potential energy. And when the string is flat, what's the potential energy? It's got to be zero. So it has to oscillate. It has to oscillate, and it is. Before we get the full picture here, let's now jump to the over here. Now what do we have here? At the turning point, what's the energy per unit length right here? There's no kinetic energy because it's at the turning point. There's no velocity. What's the potential energy? I know this seems strange, but remember, these 2 points here in equilibrium, how much are they stretched here? They're not. So there's zero energy. Zero energy per unit length, right? In the little segment here, there's zero energy at this point in time. What happens when it comes down and it's passing through the origin? What's the potential energy? Yeah, in fact, the potential energy is always zero here. Remember over here, the kinetic energy is always zero, and we have potential energy that's oscillating. Here, it's the opposite. We never have any potential energy, but the kinetic energy is going to oscillate. So these are kind of like flipped images. And the total energy has to be a constant. So what's happening here, and it's not, I don't think it's obvious. First look at this. Energy is flowing back and forth here. Energy is flowing back and forth. The total energy has to be a constant. But right now at this point, there's a concentration of energy here. There's zero energy right here at this point. And then as the string comes down, this energy flows as it must, because these pick up kinetic energy. Where does that energy come from? It comes from the rest of the string. So if you analyze this and you actually look at the flow of energy, you'll see that after it goes by the turning point here, the energy flows into here, and then when it goes by equilibrium, the energy flows. There's a continual flow of energy back and forth. Total energy has to be constant. We derived this formula in class. Remember the 1/4? Because not everything is moving at the maximum velocity. This is the maximum velocity. So we know that, we don't need to I didn't need to do this. We know this from a previous part. Remember, it's the 6 centimeters per second. So we can calculate it. Okay? And you can also, we looked at this from different perspectives. You can also just integrate this. The total energy has to be a constant. This is a closed system with no dissipation. The total energy absolutely has to be constant. So you can evaluate this. You can integrate this at any time to get this total energy. That's another way of doing the problem. Okay, any questions? Okay.